So we will continue our discussion. Let us see where were we. So we had discussed about this physical consistency and overall balance. Before that, we had discussed some of the other things, profile assumptions, what are unphysical profile assumptions, means what are profile assumptions which will not give correct solutions, and what is what is a suitable profile assumption. Then we have seen two requirements of discretization, which are physical consistency and overall balance. Physical consistency means that the solution should be physically correct. It may be approximate, means it may not be very accurate, but still it should follow all the rules of physics, laws of physics. And second one was the overall balance, means all the conserved properties should show conservation. For example, heat flux, mass flux, momentum flux, these are all conserved. So energy is conserved, so momentum is conserved. So that should come out as a even in the discretized equation, even if the grid is very coarse. So we'll see couple of things, couple of additional things. In the discretized equation, if you look at the discretized equation in finite volume method, where was the final discretized equation? This one. So this was the discretized equation, okay, where for any point P, which is a grid point representing a control volume going from small w to small e. For that point P, the variable, any variable like temperature can be written as APTP equal to AET, where E is the neighboring grid point representing the neighboring control volume, and plus AWTW, where W is the other side neighboring grid point representing the other side neighboring control volume, plus B, which is S into delta X, which takes into account the source term. So in this equation, generally AP, AE, AW and B will be known, and the unknowns will be TP, TE and TW. So for n number of points, we will have n equations, one for each point, one equation for each point. So n equations will be there for n unknowns, and we will be able to solve them together to get the final solution. So for this case, we will be able to find the temperature at all the points. Okay. Now, when we are considering that this A values, coefficients are known and this B is known, what I mean is that so AE is KE by delta XC, AW is KW by delta XW, and AP is equal to AE plus AW. So KE and delta XC should be known. Similarly, KW and delta XW should be known. So if you remember the geometry that we had drawn, delta XC is just a geometrical parameter. It is the distance between the adjacent grid points, between the grid point which we are concerned with, which is P, and the east side adjacent grid point E. Similarly, delta XW is the distance between P and W. So this should be already known after the grid has been generated by whatever software you use for generating. If I write a code and generate the grid, that is also fine. If I use a software for creating the mesh, it may look nice in the GUI, but ultimately what it is doing is it is creating all these coordinate values. What is the center point of a say control volume? What are the distances with neighboring control volumes? All these are created internally and stored in arrays. So there is no problem with the geometrical distances. They are already known. So the things that are left are this interface conductivity. Okay, the conductivity at the east interface, and the conductivity at the west interface. So if the material is same, obviously the conductivity can be assumed to be constant. if we ignore that it's a function of temperature. If it's a function of temperature, it becomes non-linear and becomes much difficult to solve. We have to resort to iterative solution. But otherwise, if it is just a normal material, single material with constant conductivity, then there is no issue. It will be known and we can use that. The problem comes when there is a change in conductivity from one control volume to the next control volume. Okay. So say for example, I am not feeling well. Anyway, say for this control volume, this is some conductivity. Okay, constant conductivity for this control. This is some material with very high conductivity. And from W to E for the next control volume, pth control volume, this is the conductivity. Conductivity, remember, are stored at the center. So we have the conductivity value here as say kW. Okay, I am unable to write with my mouse here, but this is known. K capital W is known. Similarly, K capital P is known. Okay, so we want to know what should be the conductivity at the interface. Obviously, you cannot just take constant conductivity in both the cases because then there is a jump condition. So either what we can do is we can linearly interpolate. We can take the average of Kw and Kp and find out the interface conductivity. Whether that is good or not, that we have to check. Okay, we will see now. This is one thing that is important. The other important thing is the source term, so which gives rise to this term B, which includes S into delta X. So if S is constant, again there is no issue. If S is not constant, if it is linear, then also we will see that it is not difficult to tackle that case. However, if it is quadratic or of higher order, then we have to resort to uh, some simplification, okay, which is known as linearization. So what is this linearization that we have to study, and why is it required? So linearization basically is required so that you can remove that higher order dependency and write the terms in terms of linear terms. Anyway, which will come to it later. So if we can tackle these two things, conductivity and source term properly, then everything is almost like we will be able to solve any type of equation which gives rise to this type of discretized equation. Okay, so any governing equation, conductivity, like conductive heat transfer with source term, we will be able to solve. Okay, so all the possibilities we are accounting for. Then we will go to the next type of next additional term, which is the unsteady term. But before that, we want to tackle the steady state conduction equation with source term properly. So now this for tackling this, okay, for treating this K and S, let us first consider the K. Okay. So as I was saying, if K varies over the domain, okay, if it is like a composite material, so there is say something, just take like a screwdriver or some metallic bar with a wooden handle, metallic pan with a wooden handle. So where one grid ends at the metal part and the other, so one control volume ends at the metal part and the other control volume starts at the wooden part. Okay, so there is a drastic change in conductivity. Okay, so how to tackle the interface conductivity in that case? So as K varies over the domain, say K varies over the domain, okay, position independent K, as all the parameters in a CV is represented by their values at the grid points, which is at the center of the control volumes. Okay. So K is defined, K is also defined at the center of the control volumes at the grid points, but no K is defined at the interface. Okay. Our task is to find out what should be the value of K at the interface between two control volumes. What is the suitable value of K? So let us again draw this same thing, 1D conduction problem. two control volumes. This is the pth control volume going from small w to small e. And next one is the eth control volume going from small e to say small ee. I have not mentioned it. It's not necessary. Okay. So what is the distance between P and capital E? It is delta xe. If you remember this we have taken as delta xe. You can still hear me, right?
Yes, sir.
Okay. So delta xe is the overall distance between the adjacent grid points. Say the distance from P to small e means from the grid point P to the interface is delta xe minus, and on the right hand side the distance is delta xe plus. So from the interface to the grid point E is delta xe plus. Okay. So we will use these terms. So this is obviously known, right? Because we know all the grid points, location of grid points. We also know all the location of the interfaces after mesh generation. So this delta xe minus, delta xe plus, and delta xe are all known. We need to find out ke at the interface. Let us call this as equivalent ke. Okay. So if we assume that delta xe plus is equal to delta xe minus, all the control volumes are of equal size and the grid points are at the center. Okay. So then delta xe plus is equal to delta xe minus. Intuitively, we feel that ke should be taken as the average. Okay. So ke should be kp plus k capital E by 2. Because this seems like the correct solution. Or in general, if it is not at the center, if delta xe plus and delta xe minus are not equal, then also it seems like we can take just the linear average, linear mean. Okay, delta xe minus into kp plus delta xe plus into ke by delta xe minus plus delta xe plus. Okay. This reduces to the upper value when delta xe minus is equal to delta xe plus. So linear averaging. So it looks like that this should be the correct choice. But let us see whether it is correct or not. Okay. To understand this, we will consider a composite material. Okay. So this composite material has an interface. One side is of high thermal conductivity, one side is of low thermal conductivity, like wood and or plastic and metal. And the interface coincides with the control volume interface. So we have generated the mesh in such a way so that the mesh, one of the mesh control volume ends at the interface and another control volume starts from that interface. So from P to E, we have one material, and from small e to capital E, we have another material. And the distances are again same distances, delta xe minus, delta xe plus, and overall distance is delta xe. Okay. So if there is a heat flux, say there is a temperature difference between P and E, there is a temperature gradient between P and E. So this will cause heat transfer from P to E, right? So there will be a heat flux from P to E. Okay. So that heat flux can be written as K into dt dx, right? So K into delta T by delta X. So some equivalent conductivity, or say for example, let us first write for this part only from P to small e. Okay. So from P to small e, conductivity we have taken as Kp for this region. Okay. So Kp into delta T means Tp minus T small e by delta Xc minus. Okay. Which can be written in in this way: Tp minus T by delta Xc minus by Kp. Okay, taking the Kp from the top to the denominator. So basically, temperature difference divided by the thermal resistance. Similarly, on the right hand side, we can write the heat flux as K capital E into T small e minus T capital E by delta Xc plus. Okay, rearranging again, you get T minus T capital E divided by delta Xc plus by Ke. Okay, so because the heat flux has to be equal on both sides, because it's just a continuous heat flux, because there cannot be accumulation of energy, no source term, nothing. Okay, so this Tp minus T small e by delta Xc minus by Kp is equal to T minus T capital E by delta Xc plus by Ke. Okay, which is equal to, if you add these two together, Tp minus Te by delta Xc minus by Kp plus delta Xc plus by Ke. Okay. Not add in the sense that I'm saying that means like if I have two fractions a by b and c by d, they are also equal to a plus c by b plus d. Okay. So similarly here we find that Tp minus T is equal to delta Xc minus by Kp plus delta Xc plus by Ke. So if we compare it with say some overall thermal conductivity, equivalent thermal conductivity, K small e, okay, and write the heat flux in terms of T capital P and T capital E. I can also write the heat flux as, if you look at this diagram, Tp minus T capital E divided by the overall distance, which is delta Xc. Okay, overall distance is delta Xc. Overall distance is delta Xc. Okay. Divided by average thermal conductivity Ke. Okay. So this heat flux should be equal to this heat flux because ultimately it's the same heat flux. Whatever heat goes, it is everywhere it is same, that heat flux. So from this we see that this denominator delta Xc minus by Kp plus delta Xc plus by Ke is equal to delta Xc by K small e. Okay. So this gives us an equation of K small e. Okay. It's a harmonic mean. If delta Xc minus is equal to delta Xc plus, if these are equidistant, then this becomes equal to 1 by Kp plus 1 by K is equal to 2 by K small e. Okay. This is harmonic mean of. So the equivalent thermal conductivity we see for a composite material, the equivalent thermal conductivity should be taken as the harmonic mean of the conductivity of the two materials on either side. Okay. So K is equal to 2 by 1 plus Kp plus 1 by Kp plus 1 by Ke. Okay. So this from physics, it seems that this is the correct solution. Okay. Instead of taking the linear average. So instead of taking K is equal to Kp plus Ke by 2, if we take K is equal to 2 by 1 plus 1 by Kp plus 1 by Ke, this should be much more accurate. Okay. So this means that harmonic mean is a better approximation for the interface conductivity Ke. Okay. So it does not mean that the linear mean will always give wrong results. In most cases, you will see that linear mean also gives the correct results. Okay. However, what will happen is that if you want to get accurate results, you need very fine grids near the interface. Okay, very fine grids so that the change in temperature is more accurately captured. Okay. If there is a change in thermal conductivity, then you need very fine grid near the interface. Let us look at a situation when this linear mean actually is not suitable. Okay. And why this harmonic mean is suitable. Okay. We'll consider a limiting case of this. We consider that this material has a very high conductivity like a metal, and on this other side it's like an insulator. Okay, very small thermal conductivity. So Kp is much larger than Ke. So our arithmetic mean will give us K equivalent Ke equivalent conductivity is equal to Kp plus Ke by 2. Because Ke is very small as compared to Kp, we can ignore Ke. Okay. As Ke tends to 0, we can just write this Ke as Kp by 2. Okay. So this itself is wrong. Why is it wrong? Because if we have, because Kp is quite large. Kp is has a very large value because we are considering that this is a material with a very large thermal conductivity like a metal. So Kp by 2 will also be very large. It means that if we use the equivalent thermal conductivity for calculating the heat flux between P and D, okay, like this equation, Q dash is equal to Tp minus T by delta Xc by K. If K is quite large, you will find that there is lot of heat flux. Heat flux is quite large. Okay. But what will be the case in real life? If one of the material is insulator, the overall heat flux will be 0. Okay, or very near to 0. So the insulator actually governs the heat flux. Okay. That's why this arithmetic mean is wrong. So it is wrong as if K tends to 0, there cannot be any heat flux. Okay. For small k should be the controlling factor, not Kp. But we are seeing that there is no mention of Kp becomes the controlling factor. So in this case, the arithmetic mean totally fails. Okay. So let us look at what will be the case with harmonic mean. If we take harmonic mean, so remember the equation of harmonic mean, k is equal to, so this equation let us consider. 2 by k is equal to 1 by kp plus 1 by k capital E. Okay. So if p is much larger than E, 1 by kp, so if kp is much larger than ke, 1 by kp is much smaller than 1 by ke. So 1 by kp can be ignored. Okay. Assume to be 0. So 2 by k small e is approximately equal to 1 by k capital E. Okay, or k small e is equal to 2k capital E. So in this case, we see that the overall conductivity is governed by the conductivity of the insulator. Okay, if k tends to 0, its overall conductivity will also tend to 0. Okay, and if k is very small, then you can find out that so what will happen is that what is the equation? So anyway, what will happen is that delta xc by k, which is the thermal resistance, this term. Okay. So delta xc is by k will be equal to, so because k is equal to 2k capital E, it will be equal to delta xc by 2k capital E, which is equal to half delta xc by k capital E. Okay. So half delta xc is the distance, this distance, by k capital E. So this is the thermal resistance of this part. Okay. So the overall thermal resistance is equal to the thermal resistance of this part. Obviously, this should be true because the other part has almost zero thermal resistance because of high conductivity. So the thermal resistance of this part should be equal to the overall thermal resistance, and that is what we find. So harmonic mean gives us the correct approximation of the interface conductivity. So to summarize this point, in many cases, linear average will work, and we take also linear average in many cases. But it is always better and on the safe side to take harmonic mean for all the cases, because if there is sudden jump at the interface, say I have metal on one side, so many of us are working in phase change materials. Phase change materials have low thermal conductivity, and we put some metallic films or foam or something, metal shell, to increase the average thermal conductivity. So there is a junction between the metal fin and PCM, phase change material. So if this is the case, and if we do not take harmonic mean, if we take just linear mean, there is a chance of error, or we have to take very fine grids. Okay. If we take harmonic mean, it will give us much more accurate calculation at the interface between the metal and the phase change material. Any questions on this part? No questions. So this should be clear. Okay, when you are writing your own code, you can see that this is a proper choice of conductivity. The second point that was left to discuss, and the only point that is left before we go into additional terms. So we are at this point, we are studying 1D heat conduction equation with source term. We have still ignored the unsteady term and the convective term. So next we will see how to include the unsteady term. Convective term is more difficult to include. That we will see in the next chapter. Okay. So here there are no chapters, but chapter in, I mean that book wise there are chapters in Patankar book. So all this is part of one chapter. Anyway, treatment of source term. So if there is constant source term, there is no issue. We get this solution. Means this discretized equation. APTP is equal to AT plus AWTW plus B, or B is equal to S into delta X. Okay, there is no problem. We have already seen how to incorporate this in the discretized equation. So the next complexity may come if the source term is not constant, but it's a linear function of t. So why we are writing this linear function separately, and we will consider all the other functions like quadratic, cubic separately, because there are some terms which are dependent on t. Okay, there are linear terms. So we can include a linear function of source term. So if source term is a linear function of t, we can include some of the terms in the sum of the other terms without too much modification. If it becomes quadratic, if the source term becomes quadratic function of t, then we cannot do that. Then we have to resort to linearization and iterative solution. But if it's a linear function, it still is easy to solve. And that's why we are considering it separately. Say s is a linear function of t, which can be written as some constant part sc plus some linear part, okay, sp/Tp, okay, where Tp is the temperature of the grid point. Okay. So we are assuming that for calculating the source term, we are assuming that the temperature remains constant in the control volume. This is different from the profile that we have assumed for calculating the interface heat transfer, right? So heat flux at the interface, we have assumed, for that we have assumed that we have temperature profile like this, going from P to T, and on the other side from TW to TP. But in this case, we are considering that for the entire control volume, temperature is Tp. Okay, for the entire control volume, the temperature is Tp. Draw in a better way. Not from there. For this control volume only. Let me use some other color. Similarly, for this control volume, this is the temperature. So this control volume, this is the temperature. We always know the temperature at the grid points, or we are calculating at the grid points, right? So in this case, the profile assumption is this, and this. So there is a discontinuity at the interface, but it does not matter because for source term, there is no need of any continuity at the interface. And this profile assumption is only for the source term, not for calculating the flux. For the flux, we still have this linear variation. For the source term, we can take constant. We could have taken something else also, but because constant is the easiest to take, we are taking constant temperature. Okay, because it is still correct. S is equal to SC plus SPTP for the grid point P. So coming to the integration to the equation, if you remember how we had derived, let me increase the size somewhat. d dx of k dt dx plus s equal to 0. This s now we are saying that it is not constant. It is SC plus SPTP. Okay. So for the grid point P, we had integrated going from the west to the east side. So from W to E, d dx of k dt dx dx plus from W to E s dx. Okay. So this first part resulted in this term k dt dx at east minus k dt dx at west. So the flux terms. And the second part will now result in, so instead of SXC minus XW, it will now be SC plus SPT going from west to east into d, like integral of that into dx. Okay. Now we will assume that piecewise constant temperature profile for each control volume, as I have stated. So very important to note this. Okay. So this, for this flux terms, we are considering piecewise linear temperature profile between the grid points. And for the source term, we are considering piecewise constant temperature profile for the control volume. And this is possible because we can assume different profile assumptions can be used actually, as long as it is physically consistent. So for this case, there is no need of any continuity of temperature at the interface, so we can take this. Okay. We could have taken the other one also, but it would have led to more complexity. Okay. So now after integral, after performing the integration, we are left with And after taking the profile assumption, we are left with this form of the equation. Ke into T minus Tp by delta Xc. Okay. This Ke into Tp minus T by delta Xc, this distance, minus Kw Tp minus Tw by delta Xw. Now we know how to take Ke and Kw. Okay, and delta Xc and delta Xw are known. Okay. It's the same form of the equation. This part. Only instead of S into delta X, now we have Sc plus Sp Tp. Okay, because now T for this control volume from Wt, T is equal to Tp. Okay, because we have taken constant T. So we can integrate it as SPTP into delta X equal to 0. This is the only change as compared to this. Okay. So now we can again write this in the same form as previously. If we take this SPTP into delta X term along with all the other TP terms. So we have two TP terms, Ke by delta Xc plus Kw by delta Xw. Okay. If we, so that will go to the right hand side. So along with that, if we take this SPTP to the right hand side, SPTP into delta X to the right hand side, our AP will now have. So if, what is AP? Remember, AP is the coefficient of TP. So Ke by delta Xc, which is AE, plus Kw by delta Xw, which is AW. So AE plus AW, like previously. Okay, like previously. Minus, because this will go to the other side, minus SP into delta X. Okay, because that is also coefficient of TP. Minus Sp into delta X. So AP will become like this, AE plus AW minus Sp into delta X. AE will remain same, Ke by delta Xc, AW will remain same, Kw by delta Xw. And B will be similar to the previous term, but instead of S, now it is only the constant part, Sc into delta X. Okay. So again, we can solve this exactly in the same way, using the same solver. Only difference is that our coefficient values are different. A is same, sorry, AW is same, but AP is different, and it will depend on what is the value of SP. Okay, so this SP will be a known quantity because it will be given how the system varies linearly. So it can be that some temperature dependent source term. Okay, so with temperature it is increasing the energy generation, and this B is also known. So everything is known. So we can supply all this to the solver. So we'll have n equations and n unknowns, and we can solve it exactly using the same solver to get the correct result. Any questions? No questions. It is clear what I'm trying to say.
Yes, sir.
Okay. So now the other part is that if S is a non-linear function of t, if it is not a linear function, then it will become something like Tp square or Tp cube type of term will be there. But there is no Tp square term in any of the other terms. So it becomes non-linear. Okay. That we have to tackle using iterative method. We have to linearize that equation, which is known as source term linearization. We will study somewhat later. Okay, somewhat later means just after studying another topic. So if S is a non-linear function of t, it needs to be converted to linear form. This is known as source term linearization. Okay, so before going into source term linearization, one point that we will study, there are a few rules. Okay, rules means that these are not hard and fast rules, but more you can say more like guidelines. Okay, for finite volume discretization, and these guidelines have been developed long time back based on the 1D discretization, but still give us good insight about more complex problems like 2D or 3D problems. Okay. That's why we study these fundamental rules. Again, I'm saying these are not laws. Means it's not that if you violate this rule, your answer will always be wrong. But these are guidelines or good practices, you can say. Some of them has to be correct, has to be followed, like the first point. Some of them are good practices. So there are 4 rules which are outlined in Patankar. Okay, 4 means he has written the book, he has outlined in that way, and we follow that pattern. It could have been different also. Okay. First one is the most important one. So just to summarize what I have written here, although these rules are defined based on 1D steady state diffusion type problem, like the problem we have studied, they give insight on discretization of general equations like 2D or 3D equations also. If you follow the rules, chances of getting correct solution is better. Okay, so what are these rules? By the way, I have already set the question paper for this exam, okay, because we have to submit by tomorrow. So the main focus should be you should go through the notes and try to have a good understanding of whatever we have discussed. Okay, obviously there is not much scope for numerical problem in this course. Whatever practice is required, hands-on practice, that we will get by solving the assignment and doing the project. Okay, there is no point in giving you by like solve a problem by taking 5 points or 6 points and doing hand calculation. It's just a cumbersome process. It can be easily done in a computer by hand calculation. It's time consuming, but it does not give too much insight. So that's why we are not focusing too much into those type of problems. It can be artificially created. I can easily create a problem. Like there is a 1D heat conduction problem and you are taking 3 grid points and you have to solve this with some boundary condition. And you have to find the value of temperature at these 3 grid points. It will not be difficult to solve, but it will be time consuming. So your main focus should be on the understanding part. Okay. And mostly theoretical type of questions may be there. Syllabus I will clarify after. In the next class I will clarify. Somewhere in the next class I think. Syllabus will be up to that. Let me check. Most probably up to this point, but not sure. Maybe even less also. We have to see. Up to this point or up to this point. We'll try to go till that page. No, I think it should be done. Just before the numerical solution. So up to 103. This should be a syllabus. Hopefully we will complete it, obviously. I will give you another assignment also. So basic rules, okay. So we were discussing. So first is that physical consistency of fluxes. If we are solving energy equation, it is heat flux. If we are solving some diffusion of chemical species, is the flux of the chemical species. Okay. So similarly, if it is flow, it's the momentum flux. So flux should be consistent. Means the flux value of flux from one side to the other side should be the same. There cannot be any jump in the say heat flux at the interface. So physical consistency of fluxes at all the control volume phases. So whatever are the neighboring control volumes, all the phases with the neighboring control volumes should have physical consistency of fluxes. So this will depend or this will govern how the profile is chosen. So profile should be chosen in such a way that there is no discontinuity of flux at this control volume phases. We have seen one example how to take appropriate profile. Okay. There can be other appropriate profiles also. The important thing that is to be noted here is that this interface flux it's a independent quantity. It does not belong to any particular control volume. Okay. We cannot say that when we are solving for P control volume, we have a different flux at the interface. And when we are solving for W control volume, we have a different flux at the interface. The flux is the flux, is the physical flux across the interface. Whether we solve for W control volume or P control volume is the same flux. Okay. The interface flux does not belong to any control volume. As a result, it should not be governed by the property of any individual control volume. So if the flux is not, say it does not belong to the pth control volume, the flux should not be only governed by the Kp value. Okay, it should be governed by some mechanism which takes into account both the control volume properties. Okay. The interface flux does not belong to any control volume. For example, it should not be governed by the grid point K for a particular control volume. So it should take into account the property of both the control volumes. Okay. Except the limiting cases, of course. The limiting cases like what we have seen. So this is a very important property. This has to be followed. Okay. Otherwise, it will give to physically inconsistent solution. Second rule is that all the coefficients of discretized equation must be of same sign. Okay. What is this, or why is this important? Let us try to understand. So this is our equation, right? APTP equal to AT plus AWTW plus B for this type of discretization. Okay. So remember, so this figure you should remember very well. Okay, all the dimensions and everything. So again, to reiterate, pth control volume goes from small w to small e and has a length of delta x. The distances between adjacent grid P and E is delta xc, and between W and P is delta xw. Okay. So capital letters are used for grid points, small letters for interfaces. AE is KE by delta XC, AW is KW by delta XW, AP is equal to AE plus AW minus SP delta X, assuming linear source term, plus B, where B is SC into delta X. Okay. So the general case with a linear source term. So let us assume a simple case now. Okay. SC is 0 and SP is 0. There is no source term. So our equation becomes APTP is equal to AT plus AWTW, and AP has to be equal to AE plus AW. Okay. Let us consider this equation. Ten TP is equal to 15 TE minus 5 TW. Okay. So AE plus AW is equal to AP, that is satisfied. 15 minus 5 is equal to 10. Okay. However, all the coefficients are not of same sign. So we have said that all the coefficients should be of same sign. But here we see that this AW is negative. AE and AP are positive, AW is negative. So this is not correct. This is inconsistent because if TW increases, okay, say you have a boundary. So if I have a domain like this, and this point temperature is increasing, so obviously its effect should be that this temperature should also increase. It cannot happen that if this temperature increases, this temperature decreases, because there is no source term also, or no negatively dependent source term. So if this temperature increases due to conduction, this temperature also has to increase. But what we are getting from our equation, if TW is higher, TP is lower. It means that it is physically not consistent. Okay, this is physically inconsistent as TW increases, TP decreases. In this case, which cannot happen. Increasing the neighboring grid temperature should increase the temperature of the grid point, which I have just discussed. Also, another thing that we note here is that, okay, say some values are given. Okay, say TE value is what we have taken 10 and TW is 100. Okay, so 10 into 15, 150 minus 5 into 100. 500, so minus 350. 10 TP is equal to minus 350, or TP is equal to minus 35. So it is not possible. It is not bounded. Remember that without source term, the value in between 2 points has to be, the value also has to be between these two values. Okay, they are governed by they have to be bounded. But our case, we are getting some value which is beyond the value of E and W. Okay. So again, it is not possible. So we see that situations may arise where this negative sign or the opposite sign is causing problem. If this was a positive sign, this should not have caused problem. So you can say that how is it possible to get negative sign because k and delta x are positive. Okay, this is artificially created problem, but it may happen that this sign can become negative. If what can happen if this sp delta x is sufficiently large, okay, then if it is larger than AE plus AW, then this AP will become negative, although AE and AW are positive. That is again, that will give physically inconsistent solution. What will happen is that if T and TW are positive, you will get negative value of TP and it will not be bounded. And again, T and TW increases, TP will decrease. So that can happen if AP becomes negative. Okay. So it is better to have all the coefficients. Not better means it should be that all the coefficients should have the same sign. Generally taken as positive by sign convention. It does not matter if it is all the signs are negative, you can just remove the negative sign to make them positive. Okay. Whether all the signs are negative or all the signs are positive does not matter because it's the same thing. But generally it is written in the positive form because of sign convention. Any questions here? No questions.
Sir,
So let us.
question.
Yes, you have a question?
Sir, this is valid only for conduction, right?
Only for conduction. Conduction means diffusion. Means
Yeah.
any type of diffusion, chemical diffusion, momentum diffusion.
On a TW side and convection in T side, and during convection, if temperature is more,
If T is less and TP is more and flow is coming from T towards TP, that is what you are saying.
yeah, yes, sir. Two cases is coming from T, is coming from TE side also, both sides, where
So still it will be valid. Still you have to, if the signs are not correct, so see, still it has to be bounded, right? The temperature has to be bounded. Means, although I am drawing it like this, so if say if some temperature comes from some fluid comes from this side towards a higher temperature, the temperature will go down obviously, but it cannot go down below this temperature. What you are saying that flow is also coming from this side, then it cannot happen. The continuity will not be satisfied. Flow cannot come from both sides. Okay. So either flow will come from one side and go to the other side, or flow will come from other side and go to this side. Okay. It cannot happen unless there is a negative source term for the flow here. So if source terms are present, this is not valid, but otherwise it is still valid. Okay. Even if this convection is there. Means artificially you can create this velocity like from here and here, but that is not correct because where will the flow go? Continuity will be not valid. Continuity equation will be like not satisfied. So these are the two important rules you can say. So one corollary of that rule, which is can be stated as a third rule, is that if the source term is linearized, which we will see how to linearize it, but if it is in linear form, SP must be negative. Okay, SP must be taken as negative or zero. Okay, should not be taken as positive. Either we should take it to be zero or negative. Why? It is clear from here. Okay, well, let me just keep this open. Server will be doing this right. AP is equal to A plus AW minus SP delta X. Okay. So we do not know what is the value of delta x. Delta x could have be very large also. Okay. So it is better to we remain on the safe side. And if we take SP to be negative or 0, then there is no chance that AP is going to be negative. Okay, if AE and AW are positive, AP should be AP will be positive. AE and AW are going to be positive because conductivity and distance are positive. So if SP is negative, minus of negative should be positive. So there will not be any chance of this AP going to be negative. Okay, so it's like a factor of safety, you can say. Okay, so if S is equal to SC plus SPTP, SP should be made negative. In this case, irrespective of values of AE, AW, and delta X, AP will always be positive. So this is like a corollary or an extension of the second point, and it's just is beneficial. Sometimes it is unavoidable. You cannot make SP negative, then SP should be taken as 0. We will see that in linearization how to take this to be 0. It should not be taken as positive. So one final point is that if a linear governing differential equation is discretized, okay, its discretized version should satisfy the following condition. If T is a solution, T is the T field, means T is consists of all the temperature at all the points. Okay, then T plus some constant will also be a correct solution. Okay, so say the temperature here is 300, here it is 400, and here 500. Okay, then T plus some constant, say 5. 305, 405, and 505 should also be correct. So now this constant C, value of C, has to be determined, or it will become fixed if the boundary conditions are given. Okay, then this will cannot be arbitrary, because based on the boundary temperature, this value of C will be fixed, and you will have a unique solution. But without boundary condition, just by solving the equation, you get infinite number of solutions of the form T plus C, where C is a constant. Okay. So if there are no source terms, we are seeing that if there are no source terms, AP is equal to AE plus AW. Okay, or if there are more than two neighbors, always AP will be equal to AE plus AW plus AS plus AN, or whatever are the neighbors. So summation of all the neighbors. AP will be summation of all the neighbors. Okay. So if this is the case, this condition is automatically satisfied, because APTP is equal to summation of A and B T and B, and summation of A and B is A. Like, because it is equal to AP, you can just replace T with T plus C, and you will see that that equation is also satisfied. Okay. The uniqueness in the solution will come from the boundary condition. Boundary condition will give us the correct only single unique solution. However, if there is a temperature dependent source term, this condition is not valid. Okay, because obviously in that case the source term will vary with the temperature. So for T there will be a different source term, for T plus C there will be another source term. So it becomes, this condition is not satisfied. Okay, so this is another condition. So these are sometimes called as basic rules of CFD, and these are although these are derived based on the these are defined based on the simplistic problem of 1D diffusion or conduction with source term. The logic or the insight still holds true for multidimensional problem. So always, for even for multidimensional problem, it is better to take SP as negative, and it is also better to take all the coefficients as positive. Okay, and obviously flux at the boundary has to be, flux at the controllable faces has to be consistent. That is a very strict condition. If you do not do that, then there can be big trouble. Okay. Even for multidimensional problems, these points hold true. Any questions? So I think today I will stop early. Okay, I'm not feeling too good today. So anyway, we are also going quite within time correctly. We will have a few classes at the end for the presentation and stuff also. So we will stop here today. and we'll continue in the next week with this source term linearization part. And then we will discuss about treatment of boundary condition. And we will see some extensions, unsteady one-dimensional conduction problem. And 2D, I will just give it as an exercise. Okay, 2D and 3D. It will be just given as an exercise. So up to that point, we will complete. And that will be our syllabus for the exam. So then second up, we do not have too much. We can focus on other things also. Any questions? Otherwise, we'll just stop here today. One student is not present.